Hi everyone. Today we're going to study basic rules of derivative. Let's have the first rule. This is about derivative of a constant. If k is a constant, then d over dx of k equals 0. Let us see some examples. This is example 1. Y equals 5. So we have y prime equals 0. Second example, y equals negative 10. This is another constant, so we say that dy over dx equals 0. In here, we used another notation of derivative. Example 3, f of x equals pi. This pi is considered a constant, so we say that f prime of x equals 0. These are the answers for these examples. Rule number 2. This is derivative of a power function. We have d over dx of x raised to n. And this is equal to n times x raised to the power n minus 1. Provided that n is not equal to 0. Let us see some examples. This is example 1. Y equals x cubed. So the derivative is y prime equals, the power 3 here comes down as coefficient, then multiplied by x, and this x is now raised to the power 3 minus 1. Simplifying further, the power 3 minus 1 becomes 2. So the derivative here is y prime equals 3x squared. Example 2, y equals 1 over x raised to 7. Let us show that this fraction has a term with negative exponent. So we have now x raised to negative 7. Let us now apply the rule of derivative. So our y prime here equals negative 7. That is the power that will come down here as coefficient times x raised to negative 7 minus 1. So in the exponent, the negative 7 minus 1 becomes negative 8. Putting this negative exponent into positive exponent, so we have our final answer as y prime equals negative 7 over x raised to 8. Example 3, y equals square root of x. Let us rewrite this function into a fractional exponent. So we have x raised to 1/2. And then let us apply the rule of the power function. So the y prime equals 1/2 times x raised to 1/2 minus 1. In our exponent, this 1/2 minus 1 becomes negative 1/2. And then let us rationalize the negative exponent. It becomes 1 all over 2 times x raised to positive 1/2. Let us return the fractional exponent into radical form. So we have our answer to be 1 over 2 times the square root of x. These are the answers for the given examples. Rule number 3. multiplication of a constant by a function. If k is a constant, then d over dx of k times f. This f is a function. So this is equal to k times the derivative of the function. Example 1, we have f of x equals 2x raised to 5. So the derivative here is 2 times the derivative of this x raised to 5. And that is equal to 5x raised to 4. Then we will multiply the constant 2 with the coefficient 5. So the final answer is 10x raised to 4. Example 2, y equals 5x raised to negative 3. This is equal to dy over dx equals 5 times negative 3 times x raised to negative 4. We multiply 5 times negative 3 and our final answer is negative 15x raised to negative 4. These are the answers for the given examples. Rule number 4 is about addition rule. So we have d over dx of the two functions f plus g. So we have here the derivative of f plus the derivative of g. Let's see this example 1. Y equals 3x raised to 5 minus 2x cubed. So we're going to take the derivative of each of the function, just like this. So we have y prime equals the derivative of 3x raised to 5 minus the derivative of 2x cubed. So we have here y prime equals 15x raised to 4 minus 6x squared. Example 2, y equals 10x plus 7. Again, we're going to take the derivative of 10x plus derivative of 7. For the derivative of 10x, we have 10 times 1 times x raised to the power 1 minus 1 plus the derivative of 7, which is a constant, is 0. Simplifying further, we have now 10 times x raised to 0. This x raised to 0 is simply 1. So 10 times 1 is equal to 10. These are the answers for the given examples. Today, we're going to study product rule of derivative. Let f and g be two differentiable functions. The derivative of the product of f and g, denoted by d over dx of the product f times g. This is equal to f times d over dx of g plus g times d over dx of f. Or simply we write f times g prime plus g times f prime. Let us see this example 1. Find the derivative of y equals, the first function is x squared plus 1 times the second function x cubed plus 2x. For our solution, let us write the formula of the product rule. And then, let us assign the first function to be the f, while g for the second function. And for the derivative of this y, we will have this y prime equals, we copy the f or the first function, that is the x squared plus 1, multiplied by the derivative of the second function. So this is the g prime, and we have here 3x squared plus 2. Then plus, we write the g, that is the second function. So we have here the x cubed plus 2x. Then multiply by the derivative of the first function. So we have here 2x. Simplifying the product of each group, we have now 3x raised to 4 plus 2x squared plus 3x squared plus 2 plus the product of the second group here, we have the 2x raised to 4 plus 4x squared. Let us remove the grouping symbol and combine similar terms. So we have now y prime equals 5x raised to 4 plus 9x squared plus 2. This is the derivative of the given function here. We have another solution to consider, and that is to simplify first the function. We will get the product of this function, so we have now y equals x raised to 5 plus 2x cubed plus x cubed plus 2x. We can combine the two terms in the middle, so we have y equals x raised to 5 plus 3x cubed plus 2x. And from here, let us get the derivative. So we have now y prime equals 5x raised to 4 plus 9x squared plus 2. We can see here that our answer is the same with our product rule formula. Now, for example 2, find the derivative of y equals 3 minus x squared times the quantity x cubed minus x plus 1. For our solution, let us write the formula of the product rule. And let us assign the f for that first function and g for the second function. And for our derivative, we write like this. The first function here is the f, that is the 3 minus x squared, then multiplied by the derivative of the second function, that is g prime. So we have here 3x squared minus 1, then plus the g is the second function, so we have the x cubed minus x plus 1 times the derivative of the first function f, that is f prime. So we write here negative 2x. Let us simplify the products respectively. So we have y prime equals 9x squared minus 3 minus 3x raised to 4 plus x squared. Then plus the second group will be negative 2x raised to 4 plus 2x squared minus 2x. Let us remove the grouping symbol and combine similar terms. So we have y prime equals negative 5x raised to 4 plus 12x squared minus 2x minus 3. This is our final answer. Today, we're going to study quotient rule of derivative. Let f and g be two differentiable functions. The derivative of the quotient of f and g, denoted by d over dx of the fraction f over g. The answer is a fraction where the denominator is the square of g. And in our numerator, we have two products. The first product is g times f prime minus the second product is f times g prime, where the function g of x is not equal to 0. Let us see this example 1. Find the derivative of y equals the fraction x squared plus 1 all over x cubed plus 2x. For our solution, let us write the formula of quotient rule. And then we take note that the function in the numerator is the f, while the denominator is the g. So writing now the derivative, let us begin with squaring our denominator. So we write here the square of the quantity x cubed plus 2x. And then let's begin with writing the first product. And this is g times f prime. So we write here x cubed plus 2x, that is the g, times the derivative of f. So we have the derivative of x squared plus 1, we write here 2x. Then minus the second product is f times g prime. So we write here the f is the x squared plus 1 times g prime, the derivative of x cubed plus 2x. So we write here 3x squared plus 2. Let us simplify the corresponding products of our numerator. So the first group will be 2x raised to 4 plus 4x squared. Then minus the second product is 3x raised to 4 plus 2x squared plus 3x squared plus 2. Let us remove the grouping symbols of the numerator, so we will have 2x raised to 4 plus 4x squared minus 3x raised to 4 minus 5x squared minus 2. Now let us combine similar terms in our numerator. So we have negative x raised to 4 minus x squared minus 2. And in the denominator, it will just be the same. The square of the quantity x cubed plus 2x. This is our derivative. This is the final answer. Let's have example 2. Find the derivative of y equals 2x plus 5 all over 3x minus 2. For our solution, let us write again the formula of quotient rule. And we take note that our numerator is the function f, while the denominator is the function g. Writing now our derivative, let us begin with squaring our denominator. So we write here the square of 3x minus 2. Next, let us write the first product here, g times f prime. So we copy the denominator, that is the 3x minus 2, times the derivative of 2x plus 5. So we write here 2. Then minus the second product, f times g prime. F is our numerator, so we have 2x plus 5 times g prime, the derivative of 3x minus 2. So we write here 3. Let us simplify the corresponding products of the numerator. So we have the first product to be 6x minus 4, minus the second product is now 6x plus 15. Let us remove the grouping symbols of our numerator. So we have now 6x minus 4 minus 6x minus 15. Combining similar terms in our numerator, we have the final answer to be y prime equals negative 19 all over the square of 3x minus 2. This is the final answer. Let us have example 3. Find the derivative of the function y equals 2x minus 1 all over 1 minus 2x. For our solution, let us write again the quotient rule. Let us assign the f to be the numerator and the g the denominator. Our y prime now is equal to, the denominator is the square of g. So we have 1 minus 2x, and this quantity is squared. Then, let us write the first product, g times f prime. So we write here 1 minus 2x, that is the g, times f prime, the derivative of 2x minus 1, that is 2, minus the second product is f times g prime. So we write 2x minus 1, that is the f, times g prime, the derivative of 1 minus 2x. So we write here negative 2. Simplifying the corresponding products of the numerator, we have now 2 minus 4x minus negative 4x plus 2. Removing the grouping symbol of the numerator, we have now 2 minus 4x plus 4x minus 2. Let us combine similar terms of our numerator. It is now simplified into 0 all over the same denominator square of the quantity 1 minus 2x. So the final answer for y prime is simply 0. Now let us consider another solution here, and that is to simplify the function first. Observing our function here, we can rewrite our denominator, and from here we can see that we can cancel out the numerator and the denominator respectively. So the function here is now simplified into negative 1. And now we are ready to take the derivative of this function. So the derivative of a constant is simply 0. we can see here that our answer here is the same with our answer in the first solution. This is our final answer. Today we're going to study higher derivative. Suppose that you have a function, say f of x. Then the derivative would be f prime of x. We can consider f prime of x as a new function and find its derivative also. That is finding d over dx of f prime of x. This symbol here can be simplified into this symbol, and we read this as f double prime of x. And this is now considered to be the second derivative. We can show also that the second derivative is d over dx of d over dx of f of x. And simplifying this, we may show that d square over dx square of f of x. Or if the function is given as y, this is one of the most popular notation for second derivative, and this is d square y all over dx square. Using the second derivative of f, we can find the third derivative, the fourth derivative, and so on. Successive derivatives can be denoted as follows. Given the function f of x, f prime of x equals d over dx of f of x. This is the first derivative. F double prime of x is equal to d over dx of d over dx of f of x. Simplifying this, we can write d square all over dx square of f of x. And this notation is for the second derivative. We have now f triple prime of x, and this is equal to the derivative of the second derivative. So we see here we have d over dx of d square over dx square of f of x. We simplify this into d cube all over dx cube of f of x. This is the third derivative. In general, we write f raised to a power n inside a parenthesis of x is equal to d with power n all over dx raised to power n of f of x. And this is the nth derivative. Let us see this example 1. Find y triple prime of y equals 2x raised to 4 minus 3x plus 7. The y triple prime here means the third derivative. For our solution, let us begin with the first derivative. So y prime equals this 4 multiplied by 2 becomes 8 multiplied by x with the power 4 minus 1. So we see here power 3. So 8x cubed minus the derivative of 3x is here 3. So minus 3 plus derivative of the constant 7 is 0. So we will not write anymore. Therefore, the first derivative is equal to 8x cubed minus 3. Next, for the second derivative, that is y double prime equals this 3 multiplied by 8 becomes 24 times x raised to the power 3 minus 1. So we see here 2. So y double prime is equal to 24x squared. The derivative of the constant is 0. So we will not write anymore. For the third derivative, that is the y triple prime is equal to this power 2 multiplied by 24, it becomes 48 times x raised to the power 2 minus 1. So we simply put here x. So y triple prime is equal to 48x. This is our final answer. Let us see example 2. Find d square y over dx squared. So this is about second derivative of the function y equals x raised to 5 at the point x equals 2. Let's begin with finding the first derivative. So we have dy over dx equals the power 5 comes down here as coefficient. So we have here 5x raised to the power 5 minus 1, which is 4. So the first derivative is equal to 5x raised to 4. For the second derivative, we will have now this symbol. So we have 4 times 5 is equal to 20 times x raised to the power 4 minus 1. So we have here 3. So the second derivative is 20x cubed. For our problem here, we can write this in symbol as d squared over dx squared of the function x raised to 5. And we put a line here, and the subscript is that x equals 2. This is about the second derivative, and we are going to evaluate it when x is equal to 2. So this is equal to the second derivative value, 20x cubed. Now, let us substitute the value of x is equal to 2. So we have 20 times 2 raised to 3. And this 2 cubed will give us 8. And 8 times 20 is 160. This is our final answer. Today, we're going to study derivative of trigonometric functions. The derivative of trigonometric functions are, we wrote the first two, d over dx of sine x. This is equal to cosine x. Second, d over dx of cosine x equals negative sine x. The second two are d over dx of tangent x equals secant square x. The fourth one, d over dx of cotangent x equals negative cosecant square x. The last two, we have d over dx of secant x. This is equal to secant x times tangent x. The last is d over dx of cosecant x. This is equal to negative cosecant x times cotangent x. Take note that trigonometric identities are helpful in simplifying derivative. Some important but not limited to identities are tangent x equals the fraction sine x over cosine x. Cotangent x is equal to 1 over tangent x, and this is equal to the reciprocal of this fraction. So we write here cosine x over sine x. Next, we have cosecant x equals 1 over sine x. Secant x equals 1 over cosine x. Sine square x plus cosine square x equals 1. This is one of the most popular identities. Tangent square x plus 1 equals secant square x. 1 plus cotangent square x equals cosecant square x. Let us see this example. Find the derivative of y equals tangent x. For our solution, we're going to refer to this formula d over dx of tangent x equals secant square x. Now, the derivative of this function, we are going to write here y prime equals secant square x. This is the final answer. Example 2. Find f prime of x of f of x equals x squared cotangent x. For our solution, let us observe that our function here is a product of two functions. The first function is x squared. The second function is cotangent x. So we are going to use two formulas here. The first is the product rule. So we write here d over dx of the product f times g. This is equal to f times g prime plus g times f prime. Next is the derivative of cotangent x. So we have d over dx of cotangent x equals negative cosecant square x. For the computation of derivative, we write now f prime of x equals, we copy this x squared here, times, we are going to show that we will take the derivative of cotangent x later. So we write cotangent x prime plus, we copy this cotangent x, it is here now, times the derivative of the first function, x squared. So we see the prime symbol here. Let us now simplify the derivatives. So we have x squared times the derivative of cotangent x is negative cosecant square x plus we copy again this cotangent x times the derivative of x squared, which is 2x. Now let us simplify the corresponding products. So we write f prime of x equals negative x squared cosecant square x plus 2x cotangent x. Take note that the x here is a polynomial function, while the x in here is the angle of the cotangent. So we cannot put them together. This is our final answer. Example 3. Find dy over dx of y equals the fraction 2 times cosine x all over 1 plus sine x. For our solution, let us observe that our function here is a quotient. So we write the quotient rule. D over dx of the fraction f over g equals g times f prime minus f times g prime all over g squared. Next formula is the derivative of cosine x. So we write here d over dx of cosine x. This is equal to negative sine x. Next is the derivative of this sine x. So d over dx of sine x equals cosine x. We are now ready to write the solution for the derivative. So we have dy over dx equals, we will apply the quotient rule, first by squaring the denominator. 1 plus sine x is now squared here. And then in the numerator, we're going to write 1 plus sine x, that is the g function, times the quantity, which is the derivative of the numerator. So this is 2 cosine x prime. Then minus, we will copy the numerator, 2 cosine x times the derivative of the denominator, 1 plus sine x. That symbol here again shows derivative. Let us now simplify the corresponding derivatives into like this. We will copy everything except that our derivative here of 2 cosine x now becomes, we put the constant outside 2 and then take the derivative of cosine x, and that is this negative sine x. Then this negative 2 cosine x we copy here, then we take the derivative of this binomial. The derivative of 1 is 0, that is a constant, plus the derivative of sine x is cosine x. Now simplifying the product of the numerator, we have now negative 2 sine x minus 2 sine square x for this group. Then minus, for this group here, it is simplified into 2 cosine square x all over the same denominator. Please observe in the numerator that we have a common factor, and that is the negative 2. We can pull out the negative 2, so we have this negative 2 times the quantity sine x plus sine square x plus cosine square x all over the same denominator. Take note that the sum of sine square x plus cosine square x is an identity, and that is equal to 1. So we can change these two into a simple value, which is 1. So we have now negative 2 times the quantity sine x plus 1. Please observe also that this sine x plus 1 is the same with 1 plus sine x. So we can cancel this binomial in the numerator, and we will subtract 1 in the power of our denominator. So our answer now becomes negative 2 all over the quantity 1 plus sine x. This is our final answer. Today we're going to study derivative of exponential functions. First, let us define exponential function. The function y equals e raised to x is called exponential function with base e, where e is equal to 2.718281828 and so on, and this is an irrational number. We will study now the derivative of exponential functions. Let us write the formula. The first one is d over dx of e raised to x, and this is equal to e raised to x. It means whatever the function we see here, we will just copy here. In general, when we have d over dx of e raised to an exponent which is a function of x, the derivative is equal to e raised to f of x times f prime of x. Letter B, d over dx of a raised to x. This a is a value that is greater than 0. This is now equal to a raised to x times ln of a. This ln is natural logarithm. In general, d over dx of a raised to f of x, this is equal to a raised to f of x times ln a times f prime of x. Let's see example 1. Find dy over dx if y equals e raised to the function x cubed. For our solution, we write the general equation for the exponential function where base is e. This is our formula. Now, let us write the derivative like this. First, we copy the function itself, e raised to x cubed, times d over dx of x cubed. Simplifying the derivative here, we have 3x squared. Rewriting the derivative in such a way that the constant is in front. So our final answer is 3x squared e raised to x cubed. Example 2. Find the derivative of y equals 5 raised to x sine x. For our solution, we will take the derivative of this, but we should remember 3 things. Number 1, the product rule. We can see here that our function is a product of 2 functions. The first function is 5 raised to x. The second function is sine x. Second, remember the derivative of sine x. And the third, remember the derivative of a raised to x. In this case, the a is equal to 5. So with regard to our product rule, let us now write the derivative. So we have 5 raised to x times d over dx of sine x, plus we copy that sine x times d over dx of 5 raised to x. Let us copy again this line and then let us simplify the respective derivative. So the derivative of sine x will be cosine x. The derivative of 5 raised to x will be 5 raised to x times ln of 5. We can see that we have two groups here and there is common, and that is the 5 raised to x. And we can factor that out. So our final answer is 5 raised to x times the quantity cosine x plus ln of 5 times sine x. Example 3. Find the second derivative of y equals x raised to 5 e raised to 3x. In this problem, we can see that we need a product formula. Let us now solve the first derivative. So dy over dx equals x raised to 5 times the derivative of e raised to 3x plus that e raised to 3x times the derivative of x raised to 5. Let us take now the derivatives respectively. So the derivative of e raised to 3x will be e raised to 3x times the derivative of 3x. And then in here, the derivative of x raised to 5 will be 5x raised to 4. Now, the derivative of 3x will be 3. When we simplify this line, the final answer for the first derivative will be 3x raised to 5 e raised to 3x plus 5x raised to 4 e raised to 3x. For the second derivative, we're going to take the derivative of this dy over dx. And in here, we have two terms that are both products of two functions. So taking the second derivative, we keep the constant outside. So we'll have d square y all over dx square is equal to the constant 3 is outside times the quantity x raised to 5 times derivative of e raised to 3x plus e raised to 3x times derivative of x raised to 5. So this is for the first group here. Plus the derivative of this. So we write here the constant 5 outside and then x raised to 4 times derivative of e raised to 3x plus e raised to 3x times derivative of x raised to 4. Let us now take the derivative respectively. In this case, we will have this 3e raised to 3x. Derivative of x raised to 5 will be 5x raised to 4. The derivative of e raised to 3x will be 3e raised to 3x. The derivative of x raised to 4 will be 4x cubed. Let us now simplify this line by multiplying the respective constants inside. So we will have this 9x raised to 5 e raised to 3x plus 15x raised to 4 e raised to 3x. The first two terms here correspond to this group. Plus 15x raised to 4 e raised to 3x plus 20x cubed e raised to 3x. The last two terms here correspond to this group. On this line, please observe that the middle terms here are similar terms, that we can combine them. So we have 30x raised to 4 e raised to 3x for the combination of these two terms. On this line, please observe that there is a common factor. And the common is x cubed and e raised to 3x. Factoring out that common term, we have x cubed e raised to 3x times the quantity 9x squared plus 30x plus 20. This is our final answer. Today we're going to study derivative of logarithmic functions. Let us first define logarithmic functions. The function y equals log of x to base b, where b is not equal to 1 and b is a positive constant, is called a logarithmic function. On the other hand, the function y equals natural log of x. In symbol, we write ln x, is a logarithmic function with base e. Let us study now the derivative of logarithmic functions. For our formula, let's start with d over dx, or the derivative of log of x to base b. This is equal to 1 over x times the natural log of b, or ln b. In general, we have d over dx of log of u to the base b, where u here is a function of x. This is equal to 1 all over u times ln of b, multiplied by du over dx. Letter B formula, d over dx of ln of x. This is equal to 1 over x. In general, we write d over dx of ln of u. Again, this u is a function of x. This is equal to 1 over u times du over dx. Let us see this example 1. Find the derivative of y equals log of the function 2x plus 5 to base 7. For our solution, here is the formula for the derivative of log of u. Take note that our u here is the function 2x plus 5. Using this formula, we will now write y prime, that is the derivative, is equal to 1 all over the function 2x plus 5, that is the u, times ln of 7. 7 here is the b. Then times d over dx of the function 2x plus 5. Simplifying now this derivative here, we have the answer as 2. Let us multiply this 2 with this fraction. We'll just put this 2 as numerator. And this is our final answer. Example 2. Find the derivative of y equals e raised to 2x times ln of x squared. For our solution, we take note that we have a product here of two functions. The first function is this e raised to 2x. The second function is ln of x squared. We will use the product formula here. So our dy over dx, or the derivative, is equal to e raised to 2x times the derivative of the second function, plus we copy the second function times the derivative of the first function. On the next line, we're going to copy everything, and this time we will simplify the respective derivative. So the derivative of ln x squared is 1 over x squared times the derivative of x squared. In here, the derivative of e raised to 2x is e raised to 2x times the derivative of 2x. We will copy this line in the next step, but we will evaluate the derivatives respectively. So the derivative of x squared will be 2x. The derivative here of 2x is now 2. Now look at this portion of the first group. We can see that x can be cancelled with 1x of the denominator here. Here we go. And then, in the two big groups here, we can observe that there is common among them. And the common is the 2 times e raised to 2x. Factoring the common, we have 2e raised to 2x times the quantity 1 over x plus ln of x squared. This is our final answer. Example 3. Find the second derivative of y equals x squared times ln x. For our solution, we take note that here we have a product of two functions again. The first function is x squared. The second function is ln of x. So let us take now the first derivative. We have y prime equals x squared, that is the first function, and then multiplied by the derivative of the second function. Plus, we copy here the second function times the derivative of the first function. On the next line, we will evaluate the derivatives respectively. The derivative of ln x is 1 over x. The derivative of x squared is 2x. In this group, we can see that we can cancel this x in the denominator and one of the x in this expression. Here we go. So in the next step, we have now the y prime, or the first derivative, equals x plus 2x ln x. Now let us take the second derivative. So we will write y double prime. This is equal to, the derivative of x is 1, then plus, let us write the constant outside, and we will take derivative for x and ln x. So we copy first the x here and take the derivative of ln x. Plus, we copy the second function ln x times the derivative of that x. Simplifying now the derivatives respectively, the derivative of ln x is now 1 over x. The derivative of x is 1. We can see in this portion that x times 1 over x we can cancel those x. So it will be equal to 1. Now let us multiply this constant 2 in all the terms inside the grouping symbol. So we have 1 plus 2 plus 2 ln x. This number 1 plus 2 can be combined together. So y double prime is equal to 3 plus 2 ln x. This is our final answer. Today, we're going to study derivative of inverse trigonometric functions. First, let us have a review about inverse function. If f of x is defined from a to b, such that f of x equals y for all x an element of a, where it is a bijective function. Bijective means the function is one-to-one and onto. Then there exists the inverse function f raised to negative 1 power. This is the symbol for inverse, defined from b to a, such that f inverse of y is equal to x for all y an element of b. Let us also review about inverse trigonometric functions. For the trigonometric function, let's say y equals sine x. If we want to get the angle x, we compute for x equals sine inverse of y. And it follows that the inverse function becomes y equals sine inverse of x. In other books, you will see y equals arc sine of x. Let us study now derivative of inverse trigonometric functions. Let us write the formula starting with d over dx of sine inverse of x. This is equal to 1 over the square root of the quantity 1 minus x squared. By chain rule, the formula becomes like this, where u is a function of x. Second, d over dx of cosine inverse of x. This is equal to negative 1 all over the square root of the quantity 1 minus x squared. By chain rule, the formula becomes like this. Take note that there is a similarity in the derivative of sine inverse and cosine inverse. The difference is the negative sign in the cosine inverse. Third formula, derivative of tangent inverse of x. This is equal to 1 all over 1 plus x squared. By chain rule, the formula becomes like this. Fourth formula is d over dx of cotangent inverse of x. This is equal to negative 1 all over 1 plus x squared. By chain rule, the formula becomes like this. Take note also that there is a similarity between the formula of derivatives for tangent inverse and cotangent inverse. The difference is the negative sign for the cotangent inverse. Next is the derivative for secant inverse x. This is equal to 1 all over the absolute value of x times the square root of the quantity x squared minus 1. By chain rule, the formula becomes like this. Sixth formula, the derivative of cosecant inverse of x. This is equal to negative 1 all over the absolute value of x times the square root of the quantity x squared minus 1. By chain rule, the formula becomes like this. In here, take note of the similarity of the formula of derivatives for secant inverse and cosecant inverse. The only difference is the negative sign for the cosecant inverse formula. Let's see this example 1. Show the steps of finding dy over dx for y equals tangent inverse of x. First, rewrite this function to be x equals tangent y. And from here, we're going to take derivative by implicit differentiation. It means we will show that we will take the derivative of both sides with respect to x. And then, let us evaluate the derivatives respectively. The derivative of x is 1. The derivative of tangent y is secant square y times dy over dx. We want the value for dy over dx. Let us divide this equation by the coefficient of dy over dx. That is the secant square y. So the value of dy over dx now becomes 1 all over secant square y. Take note that the secant square y equals 1 plus tangent square y. We will substitute this value in here. So dy over dx is equal to 1 all over 1 plus tangent square y. We want to take the value of this function of y with respect to x by looking at our equation here. X equals tangent y. If we're going to square this equation, we will have the tangent square y equal to x squared. So we are going to substitute this tangent square y into x squared. Our final answer now is dy over dx equals 1 all over 1 plus x squared. Example 2. Find dy over dx for y equals x sine inverse x plus x squared cosecant inverse x plus 3 tangent x. For our solution, take note that there are some functions here which are products of two functions. This first function and the second function here. So we will apply the product formula. So dy over dx will be like this. For this function, the derivative now is we take the x times the derivative of the second function plus we copy the second function times the derivative of the first function. Then plus the derivative of this function is we copy the x squared times the derivative of the second function here plus we copy that second function times the derivative of the first function. Then plus the derivative of 3 tangent x is now 3 secant square x. Let us simplify this line by taking the derivatives respectively. So we have the derivative of sine inverse x is here, that is equal to 1 all over the square root of the quantity 1 minus x squared. The derivative of x is 1. The derivative of cosecant inverse x is negative 1 all over absolute value of x times the square root of the quantity x squared minus 1. The derivative of x squared is 2x. Simplifying further, this line now becomes like this. In the next line, we will simply remove the grouping symbol, and we will have this as our final answer. Example 3. Find dy over dx for the function x sine inverse of y plus y sine inverse of x equals pi. For our solution, we can see that this function here is an implicit function. So we will apply implicit differentiation. At first, let us show that we're going to take the derivative of both sides of the equation. So here is d over dx of the left side equals d over dx of the right side. On the left side, we will take the derivative of each function. Let us now begin our differentiation. On the left side, we can see that each function is a product of two functions. So we will apply product rule. For the first group here, we have now x times derivative of sine inverse of y plus we copy that second function times derivative of the first function. Then plus we take the derivative of the second group here, we copy the y times derivative of sine inverse x plus we copy that second function times the derivative of the first function equals the derivative of the right side, which is pi, and we know that pi is a constant. So derivative of a constant is 0. The next step is we're going to evaluate the derivatives respectively. So derivative of sine inverse of y is now 1 all over the square root of the quantity 1 minus y squared times dy over dx. Derivative of x is 1. Derivative of sine inverse x is 1 all over the square root of the quantity 1 minus x squared. Next, derivative of y is 1 times dy over dx. Now let us simplify this line into like this. This expression here becomes like this. This expression is now simplified into this. This expression is simplified into like this, and also this one here becomes like this. On this line, we're going to combine those terms with dy over dx in one side of the equation. It means those terms without dy over dx, we will put them on the other side. So look at the two middle terms here. There is no dy over dx on each of these terms. So we are going to transpose this to the right. Of course, the sign must be changed. So this line now we can rewrite like this. Now, the dy over dx is common for the terms of the left side. We're going to factor out the dy over dx. So we have next step to be like this. For our next step, we're going to combine these two terms into one single fraction. We will do the same on the right side. So it will be like this now. The next is, we will isolate dy over dx by dividing this equation by this fraction. It means to say, our dy over dx will be equal to this fraction here all over this fraction. Further, we can show that our dy over dx is equal to this fraction we write here times the reciprocal of this fraction. This is our final answer. I hope you learned something from this video. See you again next time.